It is recording. Great. Okay. Hi, everybody. Welcome back again to our new fall kickoff of the Machine Learning for Health Broad Seminar Series. Today, we're very, very happy to have Dr. Marzyeh Ghassemi, who is an MIT professor in electrical engineering and also computer science and the Institute of Medical Engineering and Science at MIT. Her work spans computer science and clinical venues. She holds a number of awards and accolades. I don't know if I can read them all, honestly, but I'll pick out a couple or not. Okay. You can read it on the bio. But yeah, so she's here to speak to us about the pulse of ethical machine learning in health.
Thank you. Don't read the bio, please. That's none of you need to waste your time on this. All right. I was telling Mahnaz before I started, I'm going to present some newer work in the middle section of this talk. And so I'm very happy to get comments or suggestions on improving intuitiveness for some of it, because I think some of it is intuitive, some of it is less intuitive. So welcome questions. Also, the click is very slow. I don't know why, but I'm going to click and it's going to go slowly. So my lab is the Healthy Machine Learning Lab at MIT. We work on three things primarily: constructing robust methods for fair results, evaluating whether you even need a model in a health setting. Sometimes you really don't. And then understanding how a good model might best be deployed in a healthcare setting, because just having a good model and a good person doesn't mean you're going to have a good result, right? It's about the interaction. So I'm going to start with a case study. I always start with this case study. Hopefully, none of you have seen this case study, but it's short, I promise. And this is really just to demonstrate somebody can have a really reasonable request, like, I want you to build a triage system for a hospital emergency room so that people who are not sick get sent home quickly. And then you can build a model like that. Any person in my lab or in many labs, this is not about my lab specifically, as a general capacity that most students who are part of any machine learning curriculum at the graduate level, certainly, but even at the undergraduate level, I would say, could run through this model development pipeline, not just for a healthcare problem, but for any problem. And then once you've selected your problem, they would collect data, define the outcome, develop an algorithm, and then there you go, you can deploy it. So for our specific case, where we want to develop a model that can do chest X-ray, specifically triage this diagnosis of no finding in the image, let's run through it. There are three large publicly available chest X-ray data sets that were in the United States freely available in 2021. We use those three. That's 700,000 images, good sample size. We trained a dense net, which is a kind of convolutional neural network that works really well on images and different imaging modalities specifically to predict no finding. There's no sickness in any of these images. That means they're healthy, they can go home. And then we get a performance, right? We optimize the model, we test it on a held out set. It turns out the AUC for this model is 0.859. We're done. That's a really good result. But the problem is a lot of papers, I would say most papers stop there, maybe for good reason, because even though that's a really good result, the question is, should you deploy it? That's a much harder question, right? There are many, many models that are extremely performant advice givers. And this is true for discriminative tasks like the one that I spoke about, where you have a specific thing you want to predict, and there's a right, wrong, yes, no answer. It's also true for generative tasks. But even if we pick one of the axes of this spider web graph, right? So specifically just focus in on medical question answering, you can see that, hang on, you can see that there are so many different models that use a variety of strategies, prompting, pre-training, fine-tuning, that are both open source and closed source, that at this point are doing as well as a human expert might do, right? And so in this case, maybe this is leading us to think that we really should imagine that these models should start getting deployed. I got a nice AUC. The accuracy is 0.859. If I compare favorably to a human, pretty close or above, maybe I should deploy it, right? And in fact, the FDA regulates whether you should deploy a model or not. And you can go to the FDA and say, I have a model, it does this well. And they can give you a stamp of approval to release it more broadly. There's other ways of getting your model into practice that don't involve FDA approval, but this is one way that really you could say is like the strongest stamp we have, right? The FDA also regulates other things, famously like drugs, although maybe RIP now. So what's the problem with deploying this model potentially? Well, the problem is, I've really only given you one number to indicate how well it's going to do, right? And so I'm aggregating performance. Aggregating performance is not bad in and of itself, but it can hide things. And that's something we're going to go through in many ways throughout the rest of this talk. But just in this example, let's look at the difference in the false positive rate for different subgroups in this state-of-the-art model that we had trained that was published in Nature Medicine that we're very proud of. You see that it has the largest underdiagnosis rate in female patients, young patients, Black patients, and patients on Medicaid insurance. And so if you deployed a model like this, you would have maybe rates that you were unhappy with of false positives, meaning I say that the patient is healthy and they can go home. And they actually go home and they're very sick and they could possibly die or have to be readmitted to the hospital. Okay? This is not desirable behavior. And this specific issue was hidden by aggregation. So there are ways that we can try to make sure that any model we develop is reasonable, right? That it's robust, that it's ethical. And it involves thinking really carefully along this pipeline. And I'm going to go through three parts of this pipeline briefly, just given the time. But the first and maybe most important one you might imagine is data, right? Maybe this is all from the data. That's the first thing your mind goes to, and it should, right? Because famously, data is the fuel that these models are being trained on. And one of the things our field has really, and when I say our field, I mean like AI generally, health also specifically, but just AI generally. One of the things that we've, I think, really come to terms with that we somehow haven't informed the rest of the world about, even very educated collaborators, is machine learning models are really relying on statistical biases to make predictions, which is not necessarily bad. Humans are relying on statistical biases to make predictions about traffic patterns, what we'll see next, who's going to call us, how to grade an exam. Like we're relying on patterns, but we see a very large sample of less selected data than these models are allowed to see due to constraints of what's available for them to train on. And so a state-of-the-art machine learning model will still think that, this cow in some very idyllic situation is a cow, and that this mole on skin is a benign mole, which is correct. These are both correct. But if you put a cow on the beach, the model now thinks it's an orca because it's a large black and white mammal, and most of the background is water. And it's never seen a cow frolicking on a beach before, right? This is akin to apocryphally, I don't know if this is true, so I'll say it's an apocryphal story. Supposedly, the first time that British explorers came upon a black swan, they didn't believe it was real, right? They thought it was another species. It can't be a swan because it's not the color I'm used to seeing the swan be, right? It must be different. The model is doing something like this. This is so different from what it expects that it's like, no, no, no. The background and the foreground don't make sense. I'm not using the foreground features. I'm telling like something is wrong here, right? But models can over rely on these biases. So for example, if you see marker around a benign mole, this is the same mole. The model thinks that it is no longer benign, it's cancerous. Why does it think that? Because dermatologists often put marker around moles that they think might be cancerous to watch them, make sure they're not growing. But this model doesn't have lots of examples of my skin after my kids have drawn on it in marker, right? To say like, oh yeah, that happens all the time. People get marker on them in lots of non-cancerous situations. It's not seeing a real diverse representative sample of humanity. It's seeing what it's been fed as positive and control. And that's very limited. Okay. So we all know this. We're all machine learning people, but not everybody has gotten the memo, right? And that's partially our fault. So one of the things that this sort of means is that it's cute when there's like a cow on the beach and the model thinks it's an orca. It's less cute when it's something we can't see. When the model is using a feature that is hidden to us to make a statistical bias prediction, but we can't even see that feature. It's impossible for us. And so we don't even know it's using that. We can't go back and say, ah, oh, silly model, you got distracted by the marker. Human doctors, we've tested them and this is true, cannot look at a nursing note that's had gender stripped out of it and predict somebody's gender or race. Okay, they can't. We tested them, it's not possible. But machine learning models can, and they can with really like shockingly high fidelity. AUCs of over, 0.8 are reasonable. AUCs of over 0.9 are not reasonable, in my opinion. When you look at imaging, right, medical imaging, AUCs are extremely high for detecting things like self-reported race from X-rays and CAT scans. There was a great paper from Google that showed you can predict somebody's biological sex at birth and their self-reported race, many features about a person using just ophthalmological images. There's lots and lots of papers that have been published at this point saying humans cannot do this. They cannot look at a medical image, even well-trained doctors. They cannot look at a medical image or medical text that doesn't contain specific demographic information like biological sex at birth or self-reported race, and then predict that thing. We can't do it, but models are really good at it, okay? Now you might be wondering, okay, lots of papers have been written about this, like why does it matter? Well, that is what one reviewer said in response to a paper. And so we enter my revenge paper. Okay. This paper was published last year and it made me so happy because it was really in response to something a reviewer said and it just completely destroyed their criticism. So vengeance achieved. What we did is we took the three very common imaging modalities that we had seen machine learning be applied to in healthcare at that time. This was published in 2024. So that's X-rays. And you can see here we have 6 sites where we're collecting X-rays from. And they're not just in the United States. It includes Spain, Vietnam. Okay, so this is a reasonably wide set of X-rays. And these are publicly available. So anybody can access these, reproduce the experiments. We also looked at dermatological data because it's a common application, and we looked at ophthalmological data because, again, it's a common application. In each of these cases, what we're going to do is we're going to train a deep neural network to predict a disease because that's what people do, right? We're going to train the model to predict the disease. We're not going to give it any of these attributes like sex, age, race, or the combination of somebody's attributes. We'll know them. But we're not going to give the model that, right? You could feed the tabular data in. We're not going to do that. Once the model is trained to predict no finding in a dermatological image, retinopathy in an ophthalmological image, or any of these 4 different tasks in a chest X-ray and a radiological image, we're then going to cut the final layer off and then force the model to predict somebody's demographics, their sex, age, race, or intersectional. What is that going to show? That's going to show us whether a DenseNet model that was trained with empirical risk minimization, vanilla optimization, right, to predict disease secretly learns to encode your demographic attributes in the layers, even though we didn't ask it to and we didn't give it that information. And the answer is it does. This is not that new, right? Like I have a couple papers showing this, other papers are showing this. Like this is just like reestablishing this is true, even using a larger data set, even using like a more diverse sample of chest X-rays, right? We just wanted to re-show this. What's new is we showed that the more that the model learned while you were training it to predict disease, what your demographics were, the less fair it's going to be at predicting disease for that attribute. Put another way, the more I learned who is female when I was predicting retinopathy in your ophthalmological image, the worse I will do at predicting retinopathy in female patients. Those 2 things are correlated. Okay, you can see that it's like hot on the diagonal. And this doesn't have to be this way. This is happening due to empirical risk minimization, right? The model is squeezing as much information in maybe inappropriate ways out of features, spurious features it can get from these images that it is then trying to use to do best overall, because that's what empirical risk minimization does. It doesn't care if all of the errors you make are in female patients or in Black patients or in young patients. That's what empirical risk minimization says. So can we use more modern optimization strategies to remove this? Yes, we can. This is a Pareto plot. Economists love it. I know because one of our reviewers was an economist and told us to make this plot or they wouldn't accept the paper. So we made the plot. You can see here that the x-axis is the overall AUC. It's how well you do on everybody. Okay. So you want that to be high on the right-hand side. The y-axis is the fairness gap. Not good. And so we want that to be low. And so ideally, we would have models, and every dot is a model, be in the bottom right-hand corner. And you can see, depending on the optimization strategy we use, vanilla ERM, subgroup robustness, group adversarial, each of these dots lies in a different place in this curve, right? And in this case, we were predicting cardiomegaly from a chest x-ray, and the fairness gap we're measuring is over age. But we have all the other results here as well. And you can see that these curves follow the same general shape, which is you can often go straight down from where these ERM models are and stay at about the same place on the x-axis. So your overall AUC is about the same, and drastically reduce your place on the y-axis, meaning your fairness gap goes all the way down to something that's within random noise tolerance, okay? That's great. This is a great result, right? This is a very happy thing. Like, just be smarter about how you optimize, and you can choose a model that works really well for everyone. There's one problem with this. This is what you get when you train a model on data from the same source that you're going to test it on. So when you train on the model, you train the model on data from MIMIC in Massachusetts, and then you hold out some of the patients from MIMIC, and then you test on those unseen patients from Massachusetts, from the same hospital, okay? That's not how machine learning works, right? I don't ever just make a model and then say, oh, but I'll only apply it to data from the same source, right? We're training models to be used by everyone often, or even sold to be used by the world. And so what happens if we choose the optimally performant model here and then throw it to colleagues at Stanford and say, hey, run this on your data at Stanford? Well, what happens is that you have this crazy shift, right? Locally optimal models that are the best balance of being fair and performant, are no longer optimal when you move to a new setting. For example, if I try to move to Stanford. And so in this case, you actually would have done better picking a model that was not on the curve in the original data set for MIMIC. Another model, a different modeling strategy, would have worked much better at giving you fair performant results at Stanford. And so TLDR number one is that human data is really tricky. If somebody says they figured it out, they're wrong. If they say that they've collected enough data, that's not true. Okay? You have to test models on the data from the populations they will be used on. There's no fail-safe other than this. This is just something we have to do. Any questions before I move on? All right, seeing none. So let's say we've done the best job we can with getting the best data that's available, right? It's from similar population, it has similar attributes, we're fairly certain that it's clean, great. You still have to decide which attributes the model should have, okay? There's a well-known problem with just throwing group attributes into models, and this predates AI. I want to emphasize that this is not an AI problem. This is a statistics problem, and it predates us. It's not our thing. So for decades, people have been using group attributes like sex, age, and race in clinical risk scores. So this is for estimating GFR, predicting risk of breast cancer. If you've been to the doctor and they've said, oh, give me your demographics, I want to see what your risk for literally anything is, they're probably just putting it into some additive model, and then it gives them some risk at the end. But there's a problem with this, and this is a known problem, which is using group attributes can result in worse subgroup performance for one subgroup, even though it is theoretically and empirically guaranteed to improve overall performance. Because if you're running empirical risk minimization and you have a new feature like sex that you're adding, if it made the model worse overall, the model just wouldn't choose it. It would just ignore it, right? And so it can't make the model worse overall, but it can make it worse for a specific group. So for example, if I train a logistic regression model to predict sleep apnea, if I include sex and age, it is worse for younger male and older female patients. But it's so much better for another group that you can see the overall effect is it's a 1% better model on average, right? And so this is the effect that can happen. This is why you can see, even though it's a better model overall, this aggregation can hide subgroup performance loss. And this happens for two reasons, right? It happens because of model misspecification. Maybe there's some interaction between a feature and an attribute that I can't really capture appropriately in my model. It doesn't have capacity. I don't have enough data samples to model it correctly. It can also happen because, again, in model selection, you told the model, do the best overall. You didn't force it to do best balanced across different subgroups, making sure there's not huge gaps. You just said, give me the highest number overall. Okay. But so TLDR number 2, which has many subparts, there's like 2A, 2B, 2C, and 2D. 2A, so 2 is robust learning is really hard. You need to test models on corner cases that they will fail at, but not humans, right? It's sort of unexpected that adding a demographic attribute will make you better, but not on everybody. But this is how models work. And so here, models are choosing this general performance. And that can be really dangerous for subgroups. Another thing aggregation does is it really hides generalization failure. So you don't even have to care about fairness necessarily per se. You can just care about generalization to new environments. So we wanted to check whether natural data sets that have been collected by many amazing people, there's so many cool data sets now you can use all over the world, whether they contain sufficient spurious correlations to remove what we call accuracy on the line performance in out of distribution settings. What does that mean? Well, if you train a model on this satellite data and then you test it on OOD, out of distribution data, right? So it's never seen this data, and this is like really shifted, right? It goes from America in 2002, Africa in 2009, Europe in the 2010s to suddenly America in 2016, Africa in 2017. Very different, right? Well, we would expect it to do worse. All models are going to do worse, but we would expect something called accuracy on the line, which means I expect that models, and every single one of these points is a different model, would order approximately the same between in distribution, how well they do on similar data, and out of distribution, how well they do on different data tests. Meaning, if I train a model that does well here, I would expect it to do worse in tests, but I would expect it to do better than all of the models that did worse than it in the training set. So I think things should all get worse sort of in a line, in order, okay? And you can see here, this is a pretty well-established finding, that if you train models on data like this is all you have, and then you deploy it, and someday it's being tested on data in America in 2016, the model performance will get worse, but the best model from here will still be the best model here, right? So it'll get worse overall, but like the best is still the best. The question is, if we take these data sets that I talked about previously from different countries and say those are our in distribution training set, okay? And now we want to predict no finding again. We want to predict that somebody's healthy. And our out of distribution test set is mimic. It's all of mimic, right? So we're pretending that the world all got together except for Massachusetts and trained a chest X-ray prediction model, and it got certified, and now Massachusetts gets to use it, right? And we get one sort of test, which is we get to choose a set of our test data, the mimic data, to show these in distribution people, right? That's representative of the people in mimic. And then we want to say, like, whatever model performance that we get on those people, like we expect that that's how well it'll do on the mimic data set generally, okay? And so again, here, if you randomly choose 1,000, 2,000, 3,000 patients from mimic as your held out test set to sort of optimize this data set on, you can see it does pretty well, right? Like we have accuracy on the line. How well you do in these 4 data sets it's correlated with how well you'll do in mimic. Okay. So we wanted to do something else. We wanted to find subsets of data in mimic that would give us accuracy on the inverse line, which means I want to identify subsets of patients in mimic where the accuracy of those patients is negatively correlated with in-distribution performance. So it's an adversarial way of me choosing a group of people that if you learned the very best classifier on this other data set, this model would do super poorly on these patients. And you might be thinking, well, that must be like a small group of people, because inverting performance means the best model on all those other chest x-rays is now the worst model on the people in Massachusetts. That must be really hard to do. It turns out it's not. You can choose subsets of up to 70% of the patients in mimic. That's almost 50,000 chest x-rays that exhibit accuracy on the inverse line. And these don't correspond to the ones that are the most classified, or sorry, the most misclassified. So you could be saying, well, maybe it's just choosing the hardest ones. It's not. These are patients whose specific correlations and spurious correlations are inverted from what we see in other data sets. And because there are so many of these spurious correlations we can't even see with human eyes, it's very difficult to try to disentangle them. This is not just true for mimic. This was true for a majority of the data sets that we evaluated on, which include images of wildlife, images of pathology data from different hospitals, comments from different web forums. It's a widespread issue. So finding 2B is not only do models choose general performance, but general performance really hides failures that can be very catastrophic. Okay. But so far I've been talking, about these sort of simpler cases, maybe where I'm, choose optimizing models and, I'm giving you these logistic regression examples. But surely now that we have vision language models, foundation models, right? We shouldn't have the same problems, because foundation models, which I'll call VLMs, are really flexible. They map words to images, they're trained on such large corpora, and they can do so many flexible things. Everything from generating an image to zero-shot classification, which means with no prior specification, I give you an image, and because these models have embedded both text and images to some joint space, where text and the image they describe are very close together, I can now say, again, zero shot, no prior training, that this is a photo of a doctor because it's closer to that text embedding than photo of a lawyer, for example. I can also do the inverse. And you can say, I want a photo of a doctor, a real one that existed in your training set somewhere, right? That'll embed in some place specifically, and you can find all of the images in that neighborhood and either just give them back, retrieve them, or use them again for part of generation if you're doing stable diffusion. Okay, so it's very impressive. You have all of these inference time capacities. The problem is we didn't get rid of any of those problems with vision language models. They're just as bad. And so if you want a photo of a doctor, it's often a male doctor, often a white doctor. If you do zero-shot classification or retrieval, all of the statistical biases that you might imagine society has in describing an image, those are present in these models, okay? One thing you could do, and this is very common, this is what most people do, is they take a specific approach. They say, listen, most protected attributes or concepts we want to debias with respect to, like gender, right? They fall into a linear subspace. And so let's say I want to debias for doctors. I don't want to have only male doctors generated. I want you to give me male and female doctors, right? What I would do is I would estimate where is male in the model's mind space, where is female in the model's mind space, orthogonalize, right? Draw sort of this subspace between them, and then I project them out. You sort of collapse this dimension, right? That's kind of what we do with this linear debiasing. The problem is, these concepts don't really exist in this sort of static linear way, right? These model embedding spaces can be really nonlinear. And so that means if you collapse out male and female for doctor, you could be doing something that's destructive for male and female pilots or managers. So thinking about this more carefully, if we want to generate an image of a doctor, maybe we embed right here, right? And maybe in this case, we notice that this is highly associated with race. Okay. And we don't want that. This is a real screen grab of searching for doctor on Google Images this morning. Okay. So I noticed that, when I search for doctor, there's a high correlation with race. Maybe I don't want that. So what I would do is I would remove race via this projection, right? So I do this cutting operation where instead of having it point to this part of the space, you just project it back so that it's the same point, but you remove race from being like part of the vector, right? So that's the sort of high level thing. Does anybody see any issues with this? I didn't at first, right? I didn't really see. I was like, yeah, this is like a thing we do. The issue is you have to scale all the vectors to one, right? Like you sort of stretch them out until they all exist at like the same magnitude on this unit sphere, right? And so when I removed all of the information in this point that was attributable to race, I now have so much weight on just the age axis. And so by destroying, removing, cutting out, projecting out this race attribute, I've now created a whack-a-mole problem where my association with age is going to be scaled like astronomically. And in fact, there are several papers that have shown this, that when you linearly debias using orthogonalization and projection for one attribute like race, you scale the bias on other axes like age or gender. How do we get past this? Well, one thing that we're working on now is this idea not of projecting out distances, but actually trying to rotate them. And so if you have an original embedding Z, maybe for doctor, and you want to go to a place that's close by, right, but has equidistant contributions specifically with respect to race, that's a constrained optimization problem. And so instead of orthogonalizing and projecting out one axis or one plane in n-dimensional space, you just rotate the embedding. So it goes from this dot here to this square here. And you can see it's still equidistant. Now you haven't taken the race component to zero, but you've balanced it between these different axes, and you haven't changed the contribution that age makes. Okay? So what does this mean? This means in my original embedding, right, there was a lot of cosine similarity between my embedding and race. I didn't want that. And so after projection, right, there's this diamond that would have increased the age bias, even though it's eliminating race bias. But what I can do instead after rotation is force the model to maintain age bias, whatever information it's using from any other axes, desirable or not, as much as possible, while removing this one bias I want to remove. And this is desirable because we do not know how many unrelated concepts these models are using to embed a single point. And so it's desirable when you have one thing you're trying to debias with respect to only debias that target and to leave all other contributions static until a time where you decide to address them or decide that they're valid. Okay? And so what we showed is that over many models, concepts, query types, and data sets, this approach of doing rotational debiasing rather than orthogonalization and projecting out has a very comparable performance for the targeted class. Lower is better, right? And ring here is shown as the purple diamond. While it does not have a huge effect or a similar effect to other comparable methods on the untargeted condition, okay? So it's doing what we want it to do. So TLDR 2.3, 2C, is linear debiasing, which you might imagine is the most natural thing for these big models, right? We can't change the data they're learned on. That's too crazy. They're pre-trained and we get them as they are. Let's fix them afterwards. Well, when you try to fix them afterwards, it often creates these downstream whack-a-mole problems where you hit one and you made another one pop up. And so we have to be really intelligent about how we do this association removal. Last one. Let's throw these models a bone. Why am I picking on them? Let's focus on something that isn't hard, for humans, right? Like bias is hard for everyone. Let's focus on something simple like negation. Did you realize, fun fact, that despite their flexibility, and they are amazing technical innovations that are hugely flexible, vision language models really struggle with negation understanding in kind of a funny way. Because if you ask a clip-based diffusion model, give me a table filled with food, but no chairs for the people trying to sit, there will be chairs. This is not just true for this example. It's like a common thing. People make whole like TikTok threads about it. It's very funny. And it's not just true in image generation. Remember, I said there's other things you can use, these vision language models for, and people do. When we're talking about image retrieval, if I want a picture of a dog, then all of these are fine. But if I say a picture of a dog not on grass, I don't want it to give me the pictures of dogs on grass, and it still gives me pictures of dog on grass. Okay. Same thing for visual question answering, which is sort of a newer set of benchmarks, but very interesting and important, especially in a medical space. If you ask questions about this image of a very tired, happy dog on a floor, it gets a lot of them wrong because it includes negation. Okay. And you might be wondering, these are all cute examples. There's an adorable dog in them. It's not funny when we're in a medical space, right? Because in a medical space, there is an insane amount of negation, right? And so and negation is very important. So if I say I want to alert all of the patients I've seen today that have evidence of lung opacity, that they have a certain drug that they can take, I want you to retrieve from the hospital records this patient. But if I say I need only patients with evidence of lung opacity with no signs of edema because this drug is contraindicated, it still retrieves this patient. But I did not want it to retrieve this patient. So this gets very dangerous if we're talking about negation in a medical setting, because negation is often a protective thing. And you might be thinking, like, why is this one happening, right? Like, bias makes sense. Humans are biased. We use statistical biases. The data that it sees is biased, right? What's happening here? Why is this so bad? Well, it's bad again because of us, right? Like, think about the data that these models are trained on. They're trained on image and text pairs, right? Think about any image and text pair that's ever existed in the history of humans, the internet, whatever. It's always describing the things that are present. Okay, this is a construction worker in orange working on a road. This is a black and white dog jumping over the bar. We would never say a girl in a pink dress is jumping in the air with no helicopters. Nobody describes images that way. That data doesn't exist. And so models trained on billions and billions of examples have no idea what you mean because they don't have a good way of embedding things such that negations matter because we never described things with negations. This is, again, worse in a medical setting because actually in a medical setting, there's more negations often than affirmations in descriptions of medical images. So you'll say there's no focal consolidation, effusion, or pneumothorax. There's no pneumonia, no pulmonary vascular congestion, right? Like these are things that we often negate, and then the affirmations are much smaller. And so if it's a problem in natural images, it's going to be insanely bad in medical images. And in fact, that's what we find. We create an evaluation data set that takes these images that are both medical and natural, and we have easy negation tests, right? So for this example with the orange juice, an easy negation would be includes orange juice but no straw. That's easy, very simple. We also have more natural, so harder negation tests. Contains orange juice, though straw is missing, right? That's a little harder to parse. And so we would expect it to be worse. We do the same thing for each of these data sets, creating easy and hard negations based on concepts that are related to the concept that's being targeted. So orange juice is highly correlated with straw, but there's no straw in this image. And what we find is that in natural images, state-of-the-art models that are trained specifically to do well on negation fail to understand it, both in retrieval and multiple choice question answering. And you can see on the easier cases here, the loss is, around 7%, between 4 and 7%. For the harder cases, the loss is between 18 and 23%. That's a huge drop in performance. And in a medical setting, actually, the medical vision language model results are much worse. Biomed clip drops by 24%, and Conch, which is another competitor, drops by over 30%, just when you include negation. And again, this makes sense because if we look at how things embed within these models, right, and we color affirmations, so affirmations are circles, negations are triangles, and concepts are colored according to what they are. You can see here that cat, which is a yellow circle, looks a lot like not a cat, which is a triangle. They're right next to each other. The colors are all together. There aren't like disambiguous, there aren't distances based on the shape here. And so things are often extremely close to their negation. And even in models that try to include in the contrastive learning some sense that negation is important, we don't see, each concept and then sort of circles and triangles at some respectable distance. Instead, we see this collapsed caption effect where all the triangles are moving to this point here. So this over here is a dog. This over here is a cat. This is a lion. This is a flower. And this point right here is not a cat, not a tree, not a house, not a flower, not a dog. It's just a concept for having any negation in it, which is, again, not ideal. So final TLDR for this section. Models are very hard to train in a robust manner. Okay. And that's true for several reasons. And it's in ways that we really do not expect, right? They're going to fail at corner cases that we do not realize are corner cases. Negation does not feel like it should be a corner case, but it is. And it's because they choose general performances. General performance hides failures. Linear debiasing, when you're trying to address those failures, creates this whack-a-mole effect. And even things that are really simple, like negation, still have these biases. And things like not cat look more like cat than dog, because that's the actual data these models have seen. Final section, and then we'll have time for questions. So hopefully at this point, I've convinced you that models aren't perfect, which maybe, especially if you've been to the Bay recently, you would not, have thought previously. The question is, well, can we use AI to improve humans? They don't have to be perfect. That's not the goal. The goal is not a perfect model. The goal is in medical decision making, if you're admitted to a hospital and a doctor is actually quite busy, very stressed, we have labor shortages, people are burnt out, everything is crazy. Can this model help the doctor make an informed decision? The answer is often yes, but with caveats. I just want to highlight a few findings that have really stressed that even when you have a really good model, there are issues with the interaction between a model and the human using it. So first, this is a paper from 2020. It's one of the first papers. It was in Nature Medicine. It's not my paper, looking at human-computer collaboration for skin cancer recognition. This is buried, this subfigure, in like subfigure 2J. It's like tiny. I've blown it up here, right? Because it's my favorite thing in the whole paper. What they're showing you is that the loss from incorrect AI predictions has a higher magnitude than the gain from correct AI predictions. Okay? And so if you have a bad AI model, the damage it will do to clinical capacity for performance is so much larger than the benefit of a good model. So there is a benefit of a good model, but the damage that you could get from a bad model is much worse. And this is across experience levels. So you need to make sure that it's a good system. Table stakes, this has to be a really good system, okay? Moving beyond table stakes, your model is going to be wrong sometimes. If anybody tells you different, they're lying or they drink the Kool-Aid. Both are bad. And so you need to make sure that you understand how people will receive the advice and whether they're going to be susceptible to incorrect advice. In our tests of radiologists, when we gave them incorrect advice, many of them were incredibly susceptible, which means every single tick here is a case that we asked the radiologist to rule on. And you can see if it's a red bar, that means we gave them inaccurate advice. If it's a blue bar, that means we gave them accurate advice. If you're this radiological expert who's participating, you got all 8 cases right. Okay. If you're anywhere here between person 120 and person 70, you got 7 out of 8 cases right. But look at the proportion. A lot of these people got a case wrong when we gave them inaccurate information. So look at all of these 7 out of 8 cases in this block that are at the same height. There are many more of them that are blue with 1 red case, and much fewer that got the 2 inaccurate cases right and then messed up on one of the accurate cases. And there are some bars here that are only blue, which means the clinicians only got the answer right when we gave them the right answer. So humans are susceptible. This is just a human thing, and being a doctor doesn't save you. Finally, the way that you deliver advice can matter more than the advice you deliver. So we did a study where we had a racist GPT bot that gave racist advice. We literally trained it to be racist. It was very bad. We have human subjects approval though from MIT, so it was ethically validated. So it gave this racist advice to clinicians and tried to convince them to call the police on minorities who are having a mental health crisis, but not on non-minorities who are having exactly the same mental health crisis. And what we found was that at baseline, clinicians and non-clinicians did not choose to call the police more on non-minorities when they were on minorities when they were having a mental health breakdown. All right, so that didn't matter. What was interesting is when we told people if there's a risk of violence, you should call the police. Those two things are equivalent. When we had the racist model tell clinicians there's a risk of violence, they ignored it and they did not call the police more often. But when we had it change its tone, same recommendation, just different tone, and say you should call the police, they listened to it and they disproportionately called the police on minorities. And so this isn't even a change in the prediction that we made. It's just a change in the tone of advice that we were giving. Rather than saying the if case, if there's a risk of violence, and we said there was, we gave them the directive, the then case, then you should call police. And that made the change, not the bias level of the model. And so having a better idea of how humans and AI should collaborate to make a better system overall is very important because humans are fallible. And you really need to test models with humans in these high risk uncertainty situations before you actually do a full deployment. If we want to move forward with ethical AI in human health, I think that there are really good ways, but we need to stop thinking about how to extend bad practices that were inefficient to be bad practices that are now somehow efficient. We need to think about AI as something that's transformative. And so there is really cool work that I think people have done that has had that insight, right? So more robust AI tools to predict future cancers are often doing better using deep learning models than prior models did, certainly. And so mammogram screening famously did not work well for people with different breast tissue densities. And so researchers at MIT, Harvard, Mass General actually went around the world and got lots of data that had different breast cancer images, and they built a better screening tool using that. That's amazing, right? AlphaFold completely changed the game of, I remember when I was a PhD student, PhD students that I knew spent their whole PhD trying to predict one curve of this fold. That was their thesis, right? Now AlphaFold can do all of it. It's so cool. But this is really transformative, right? These are applications that are giving us new capacities. They're making us better at doing things we couldn't ever do before. They're not just taking a process that was slow that we designed and trying to make, for example, insurance denial faster or any of these other things that we're using AI for now. We probably don't want them to be the same but faster. And so we need to think about more transformative uses for robust models, diverse data, human action to create actionable insights in human health. Thank you.
Great. Thank you so much. That was fantastic. Um, Let's see. There are a couple of questions in the chat, but maybe first I'll open it up to if anybody has a question that they just want to ask now that the talk is finished.
I can look at the chat
Yeah,
too.
or else then let's start the chat. Yeah. So there's two at the bottom there.
So from Daniel, when you choose a model that improves fairness, are you looking at AUC on the test set? Should this new model then be evaluated on a second test set to demonstrate out of sample prediction? Yes. So depending on the paper that we discussed, standard common practice is to have a validation set and then a test set. Okay. And so your validation set is where you do all of your splits and you try to force the model to be as good as possible. And depending on the setting, sometimes you allow the validation set to be drawn from the distribution that you're going to test on, right? So you don't get to see real data from, Massachusetts in the case of one of the papers, but you get to see, something that's similar, right? And so depending on what you're trying to test, like what you're trying to evaluate, you stratify what is in your test set differently. And these are all really stress tests that we use for benchmarks. It's implausible to me to expect a model to do well on data it has never seen. And it doesn't make sense to me. And I think we've gone a little too far with our expectations about generalizability. Um, and so I think depending on what you're trying to stress test, you use your validation and your test set differently. But you are correct; those should always be separate. You shouldn't be allowed to iterate on a test set. I see another question. Do we have an understanding of the types of features that are predicted of demographics, correlated with outcomes and treatment pathways? Yes. So we do have an idea. So for medical notes, it's using the way that clinical staff write about different people. Okay. And these are subtle, so you might not pick up on it, but the model does. If you say the patient claims they're in pain, not the patient is in pain, that patient is a woman. Because we don't say that men claim they're in pain. We say that men are in pain. But if it's a female patient, then the clinical staff says patient claims she's in pain or they are in pain because we removed gender in this case. So the model had to guess. If we say that a patient, that the procedure was, an invasive one and they're tolerating it, then that patient's probably white. If we say that the patient was being difficult with respect to an invasive procedure, they're probably Black. These are things the model discovered, right? Like these are not things that doctors were able to pick up on when we tested them on being able to look at a note that had been redacted and predict these things. But over millions and millions of examples, the model has learned you speak about certain people certain ways. There's also some really sad things. Those are sad on their own, but there's some even sadder things, in my opinion, which is if you mention the skin-based presentation of illness at all, the patient is white. Because I think it's only now like 8% of all examples in all medical textbooks of any skin-based presentation of illness that have melaninated skin. And so what that means is a majority of doctors do not know, not just doctors, clinical staff, do not know what the skin-based presentation of illness looks like in darker skin. They just don't know. They've never seen it. And so consequently, they don't talk about it because they cannot tell. And so if you ever discuss skin-based presentation of illness, the model's like, oh, this must be a white person. So there's things like that. With medical images, if I'm recalling the Google paper correctly, I believe there were a few things that were more salient when you use some of the image-based explainability and interpretability methods, which have their own flaws. And there were things like, in some cases, the size of the vasculature, slightly different, it's possible that depending on your biological sex at birth, you're exposed obviously to different hormonal cocktails. And so that could be correlated with the way that vasculature forms in your eye. Like there are things, but doctors cannot use those features, right? There's no like salient, aha, this vessel is this, there's no one thing. It's hundreds of different small contributions that lead to this overall prediction that's extremely, extremely accurate. For medical images, it's a difference in the image and the high end of the frequency spectrum. Okay. What that means is it's not the actual chest. You could like take out all of the biological features. It's the speckle noise pattern in the background. And that's probably because you've probably heard if your skin is more melaninated, right? You don't get as much of a sunburn. You don't, you reflect slightly more radiation in the entire frequency spectrum, right? What is an X-ray? It's radiation, right? And so more melaninated skin, which is correlated with self-reporting black race, just bounces back the X-ray, very, again, high end of the frequency spectrum, our eyes can't see it, a little bit more than less melaninated skin does. And it's super obvious to the model, right? Because it's seeing these small differences in the high end of the frequency spectrum, but we can't see it, right? And so again, it's not possible for us to see these things, but the model can. Um, Hang on. Okay, I see another one. Adversarial augmentation, synthetic data. Yes. So adversarial augmentations have limits, is what we've found, because it is possible to noise out all the things that are not biologically relevant for a specific thing. So for some things, it's biologically relevant that, for example, you're a male or female. That's biologically relevant. And for other things, it's not. Okay, pain is pain. Um, but what we've found, at least in the limited applications that I've seen people try to do on this, is it's very hard to remove these things. So as an example, let's say you want to take gender out of somebody's medical record. Okay, well, gender is inferable from height, from weight, from most labs that are taken, from almost every vital, not by me, but by a machine learning model. You would have to remove almost every like biologically relevant feature in order for me to remove gender from like your medical record because there are proxies, right? What about race? Race doesn't influence that much biologically. But due to, microaggressions and the actual lived experience of being, for example, an African American in the United States, you do have very different distributions of health conditions, access to healthcare, zip code of origin, socioeconomic determinants, like social determinants of health. And so the models are very good at guessing these things. And again, doctors aren't. And so far, what we have found is that it would be very hard to remove enough information to delete this data, this like understanding of a proxy from the model without removing things that are relevant for whatever we're predicting. Oh, is negation kind of a forever unsolved problem? It's not a forever unsolved problem. We just have to be better about doing it. I think that there's great ways to address it, and those are active areas of research for students right now. I know like at least one graduate student at MIT who is working on this. Not mine, another student. Do I have thoughts on getting doctors and patients to use better models? I've tried. Have you ever, I don't know if any of you are parents, have you ever like told your kids to do something and they're like, whatever, mom, you're not cool. Um, I think we need somebody who is relatable to the subgroup that is being targeted to say that this is not appropriate. I don't think doctors like it, in my personal experience, when a computer scientist says, don't do that. It's not like the message is not heard, right? I don't think patients like it when computer science professors at MIT say, don't do that, right? I don't think it like comes across well. And so I think we need to have better outreach as educational institutions and experts in these fields with patient advocacy groups and clinical special subspecialty areas and certifiers to say, we know this thing. It would be helpful if the whole community knew this thing and we figured out how to do it together. We also often write for ourselves, right? Like computer science is a big enough field now that unfortunately, I think sometimes we get a little bit myopic. where I'm writing a paper for the other 50 people in the world who do what I do. And I don't really expect it to be as accessible to just any person. And I think I'm working very hard, and a lot of people in my field are working very hard to try to do much more outreach, try to talk to reporters and general purpose publications to really explain what it means, not math, 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 model, 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 but here's what it really means to you. We're trying to write more generalist articles. It's difficult because it's not what we were trained for. We're not journalists. We're not patient outreach specialists, but I think it's something that's becoming increasingly needed. I don't know how long you want me to go, Danielle.
I was gonna ask, Kylie or Alex, do you guys have any in-person questions since you guys popped up on my screen, or no? Just cameras on. Or Alex, did you
No,
have one?
thanks, Danielle, and
Yeah,
thanks
sure. And then that maybe can be the last one.
important and interesting work. Just really quickly following on that, I was wondering if you have any like blog posts at this point or anything on the internet for general consumption, or if that's something you're still working on for, for a wider audience.
I don't have any blog posts. Somebody told me I need to make a blog, and I had a like Y2K moment where I was like, what? Blogs? I think so. I'm part of a collective at MIT called the AI for Society group. And we are working, we had a retreat, and one of the things that came up repeatedly was we need a way of disseminating content that is easily understandable, and a blog is probably the right way of doing it. And so we are working on making one. Yes.
Great.
It's a great idea. We just, I have not done it yet.
Well, thanks again. Really interesting work.
Okay, great. Those are some great questions. And now we're over time. So I'd like to thank again Dr. Ghassemi for giving such a wonderful talk. And I also wanted to announce for the next seminar, we have Dr. Achke Shodhari of Radiology and Biomedical Data Science at Stanford. So that's going to be, it's always the first Wednesday of every month. So that's going to be November 5th at 2 p.m. So thank you very much again, and we'll see you all next month.
Thank
Bye.
you so much, Marzyeh.
Bye.